So thank you for giving me this opportunity to talk here. And today I'll be talking about, so we try to model aggregating systems using the Smoluchowski equation in the, which is by definition in the mean field limit. So this is, I will state the model, but let me first tell that I have done this work with R. Rajesh from IMSC and Colm Konautan and Oleg Jablonski from Warwick University. And also some part of an ongoing work is being done by Nana Siddharth. So these are my collaborators. Okay, so let me first say a few words about the motivation. So the aggregation occurs when two clusters just join when they meet, and fragmentation is the reverse phenomena of it. And in nature, these processes are quite common. They happen in milk curdling, blood coagulation, formation of sand grains, also formation of planetary rings. This is quite old problem, but still a lot of work is going on. For example, in a recent study, Brilliantov, they wrote a PNS paper about the cluster size distribution of particles forming the Saturn rings using aggregation fragmentation model. So this is the sort of brief motivation, and there are different approaches for this to study this problem. One is you consider what happens to the cluster size or the mass distribution of the coagulates, and you don't worry about the morphology of the aggregate. So particles can collide with each other and they form a fractal shape. For example, this is studied in some different approaches, and that can be found in morphology of aggregates in Julian's paper. But also there is another approach where you just consider coagulating of, for example, spherical liquid blobs, where the just the size or the mass is the relevant parameter. So in this talk, I will discuss about the cluster size distribution. So I will take the first approach for a particular class of kernels or rates using the Smoluchowski equation. Okay, so the assumptions which goes behind the Smoluchowski equation are the following. So we assume spatial homogeneity. The system is well mixed, and this is essentially the mean field approximation. We also assume bimolecular reactions, so the system is sufficiently dilute so that higher body, three body, for example, interactions are negligible. And also, as I was stating, the aggregate mass is the only dynamic variable. Shapes of them play a role in this Smoluchowski equation. Okay, so what we did, we studied a system of particles that are undergoing two-body collision, either coalesce to form a single particle or are removed from the system. So this is the removing of the particle from the system is a limit where is considered as a different model, albeit similar to a model where you introduce a hard cutoff. So particles are aggregating. If the mass of the aggregate becomes higher than a certain mass, then you remove the particle from the system. So this system, the system is driven to a steady state by a constant input of particles. Otherwise, they will just form a big coagulate. And we took the following general class of kernels, M1 power. So M1 and M2 are the masses of the coagulating particles. So we take this class of kernel, and where nu is greater than or equal to mu. So for example, if you take mu equals to nu equals to 0, then, and for generally mu equals to nu, this kernel, the Smoluchowski equation is exactly solvable. Also mu 0, nu 1, that is the sum kernel. You can find the exact steady state mass distribution for that. And if both of them are 1, the product kernel, that is also exactly solvable. I have, so I will just state, yeah. So this is for the general aggregation case. The mean field Smoluchowski equation. So we have studied a mean field Smoluchowski equation using relation between moment and singular structure of the generating function, also numerical solution and exact solution of solvable limits. So essentially we found the exponents characterizing the mass distribution for small and large masses. Okay, so before I go into my model, just let me say a few words about gelling. So what a gel means for this kind of systems is, in finite time you have a big mass cluster which is a finite fraction of the total mass of the system. So that is defined as the gel here. So for example, if the sum of these two exponents mu and nu, let's call that beta. If that is greater than 1, then we know that we have a gelling kernel. So for example, the exactly solvable product kernel for which mu and nu are both 1, there you find a gel at finite time. In this gel state, a non-zero fraction of the total mass coagulates into a single cluster. Now to regularize this behavior, you can say that I introduce a mass cutoff. So if the mass of the coagulates becomes higher than that mass, then the particle is just removed from the system. Otherwise, you can also introduce a collision dependent evaporation rate. So when the particles collide, there is a probability with which the particle can evaporate from the system, and that essentially introduces a mass cutoff, as we will see. So this is our model. So let me just tell you this is the Smoluchowski equation we are talking about. So the rate, so nmt is the number of particles of mass m at time t, and this is a balance equation or the master equation. So this depends on the coagulation. So this is the aggregation part of the rate equation, and if you take just the 1, then actually this also corresponds to the aggregation. So particles are aggregating together, and with a small rate lambda, small compared to 1, the particles also can evaporate from the system. So this part corresponds to the evaporation, and there is a source of unit mass which we will call monomers. So this is the equation which we want to study. So for general mu and nu, and we want to study for this class of kernels, for general mu and nu, this cannot be solved exactly. We want to find the steady state mass distribution. Yeah, so this part we will take to 0. Okay, so let me now tell about the exact solutions. So when mu is equals to nu, in this case the steady state mass distribution Nm can be exactly solved and is given by this form, where the mass cutoff capital M, as you can see that you don't have to introduce a hard cutoff here. You get a cutoff which depends on the evaporation rate. So in the asymptotic limit where M is much larger than 1, you get a power law of a steady state mass distribution which is minus 3 plus beta by 2. Beta is mu plus nu, where as mu is equals to nu, it is equal to 2 mu here, with an exponential cutoff. So you will get a steady state mass distribution with the power law, then there will be an exponential cutoff which is given by this, and also the cutoff mass depends on the evaporation rate. So this is a exactly solvable case. Now the non-zero evaporation rate lambda results in the introduction of a mass cutoff scale that diverges as lambda to the power minus 2. So when lambda equals to 0, these results remain unchanged provided mu less than half. If mu greater than half, for general aggregating kernel, we get a gel state. But here, even if mu is greater than half, as we have introduced evaporation rate, so no gel is formed. And the important point to note is that the instability or the gel instability is removed from the system by introduction of a non-zero lambda for all mu. So thus the limit lambda going to 0 is different from the system with lambda equals to 0 for mu greater than half for this mass non-conserved model. So this is the main difference concerning this mu equals to nu case from just aggregating system. Okay. Also there is a model called addition model where big clusters just join coagulate with monomers. So if you see this kernel, then a particle of mass m1 can coagulate with another only with a monomer, not with any other masses, so which is given by this delta function. So you can see that big particles are roaming around the system and just so not roaming around exactly because there is no space, we are considering mean field, but in the mass space, so monomers are coagulating only with big masses. Yeah. So the exact solution in that case is given by this formula, and we can get the asymptotic mass behavior. So there is an exponential cutoff. We also get a power law m to the power minus nu, but the point is that the exponential cutoff, the cutoff mass scales differently with lambda. So the dependence is now lambda to the power minus 1 instead of lambda to the power minus 2 in the mu equal to nu case. So the behavior is quantitatively different here. Okay. Now, now let me go to the general case. For mu not equal to mu, we cannot find an exact solution of Nm. So to make progress, what we did, we study the moments which are defined as alpha at moment is defined as m to the power alpha Nm, and also the moment generating functions. So from the Smoluchowski equation, we can get these two relations between the moments and the moment generating functions in the steady state. So we will use these two equations to further explore what we can say. So what we assume that the time independent mass distribution has the following scaling form: m to the power minus tau with a scaling function, where we assume that m scales as lambda to the power minus y. So if you remember, y was 1 in the addition model, y was 2 in the exactly solvable case, mu equal to nu case. So we define new exponents for the large and small masses compared to the cutoff mass. So this is the form of the Nm what we assume, and there is an exponential cutoff which also comes out of the exact and numerical solutions. Okay, so from moment analysis, so if we just expand this equation, then from moment analysis we can get relation between different mass moments. So this will essentially give us a numerical method to find Nm in a self-consistent way, also to get different exponents in terms of tau s and eta s, etc. Okay, so the result which we get from the moment analysis is that first we get that eta s is greater than 0, so eta s is given as this, and we get that tau s should be bounded in between mu plus 1 and mu plus 2. So the main result from here is that the behavior of Nm depends on the value of this local or the non-local an exponent which is actually defined by nu minus mu. So if nu minus mu is less than 1, then we get a local behavior. Local behavior means that similar masses coagulate with each other. If it is greater than 1, then we get a non-local behavior, meaning that masses of very different magnitude can coagulate with each other. So and also correspondingly, the different exponents will be different. Be different in these different regimes. Yeah. Okay. So for the local kernels, we get a consistent solution only in some parameter value, and there we can find we can exactly find what are the values of the scaling exponents of the mass distribution. Yeah, and for the non-local kernel, we get a consistent solution in region 3. So we get a certain region, and there we can find the value of eta s and y, but not tau s. So tau s was m to the power minus tau s in the Nm. So to determine that, we did a singularity analysis of the generating functions. So the generating functions, as we know that they are defined as, okay, so their definition is given here. Their definition is given. So we want to find the singular structure of it, and then we want to revert it and find what is Nm. So as standard. So these actually allowed us to determine the exponents in the large mass limit, which is tau L and eta L, and as tau L plus eta L is equals to tau s plus eta s by definition, by construction, then we can also get tau s and eta s. Okay. So let me just state the results. So when tau L is greater than nu plus 1, we get the values of the exponents, also the coefficient in front of the exponent, and when the value of tau L is in another regime and nu minus mu is less than 2, we can get a form of Nm in the large mass limit. Also the exponents, we can determine the exponents. Okay, so the main point is we can determine the scaling exponents from moment and singularity analysis by in terms of mu and nu, and also the current J. Okay. And results from singularity analysis, so when nu minus mu is greater than 2, there we get different exponents. So the point is, when nu minus mu is less than 1, we are terming that as local region. When nu minus mu is greater than 1, then in the literature it was pointed out that that is a non-local region. But for this model, at least, we can find that nu minus mu between 1 and 2 is different from nu minus mu greater than 2. So there are subtleties in the even in the non-local regime for this model. Okay, now let me briefly state the numerical results. So what we have plotted, so this is for the exactly solvable case, and we can solve the coupled equation, and here we plotted nm into e to the power m by capital M, so that we can find directly the power laws. So we can see that the power laws correspond exactly to the theoretical finding of -3 plus beta by 2. Also, for the small mass behavior, for the local kernel case, we get the expected power law, and there is scaling. So this is the scaling function, the plot of the scaling function. There is a collapse of the data for the small mass case and the local kernel. For local kernel large mass behavior, we also solved this compensated mass distribution, which is a name for nm into e to the power capital M by M, so that we can find the power laws, and this is the large mass behavior. And for non-local kernel, for when nu minus mu is between 1 and 2, there also we have determined the large mass behavior, and the power laws correspond to the theoretical finding. Also there is a data collapse for them. And for non-local kernel, when nu minus mu is greater than 2, the main finding is that the exponents here correspond to the addition model. So addition model I said, so for that we have an exact solution for that. So the exponents here for nu minus mu greater than 2, they correspond to the findings, to the exponents in addition model. And there is a data collapse also for this model. Okay, so let me just summarize in the remaining 2 minutes. So what we did, we studied the steady state Smoluchowski equation, and we showed that the introduction of an evaporation rate introduces a cutoff scale m beyond which the mass distribution crosses from a power law behavior to an exponential decrease. Also the system is regularized in the sense that no gel is formed as we introduced evaporation rate lambda, but no hard cutoff. Also we find that the form of nm depends only on whether the kernel is local, that is nu minus mu less than 1, or non-local, and not on whether it is gelling or non-gelling, that is nu plus mu beta is greater than 1 or less than 1. And we find different subregimes. So nu minus mu between 1 and 2 and greater than 2, they behave differently. We also find that the nu minus mu greater than 2 coincide with that for the addition model. And there is a point, so like how to regularize a gel state is how to introduce a cutoff for this kind of systems is not very well understood. So like here we introduced evaporation rate to get a cutoff of mass, but for example in this paper Konauton, they introduced a hard cutoff and the results were somewhat different. So precisely what is the role of a cutoff in steady state Smoluchowski equation solutions, that is not yet well understood. So maybe that may be a future direction for research. Thank you. Yeah, yeah. Yeah, provided you don't have any input of monomers. So yes, otherwise it will just grow. Yeah, yeah. If you introduce a cutoff, lambda, it gives you this exponential large M and the natural cutoff. Yeah. So you see that this limit lambda coming to 0. Yeah. Is somewhat singular because whatever. So the limit is different from lambda equal to 0 case. Yes. Yeah.
But usually there is always a kind of crossover. I mean, you can always match these two behaviors. So
So for so for this case, what we find that the behavior at lambda equal to 0 and lambda going to 0 are different, but I don't know whether what sort of crossover or what will be the behavior.
this was my question, because even if they're different, usually there is always kind of a way of matching both.
Yeah, maybe.
So, for example, it could happen that the steady state is reached in finite time, or something like that, when new
So, like then actually what you are saying that is there a crossover between the gelling state and the non-gelling state, because equal to 0 is gelling, not equal to 0 is non-gelling. So if there is a connection between them, I don't know whether that can be studied if you don't introduce a cutoff, maybe. Yeah, but I am not sure about that. Yeah.
Is the steady state reached in finite time?
So we are assuming a steady state.
Okay,
we are the time evolution. No, we have not studied the time evolution. But there is a point. So Rajesh, they did a calculation that was published in 2012. So there, what they did, they assumed there is a steady state. They solved the Smoluchowski equation. Then they put the solution as an initial condition in the time-dependent solution. So after they studied, they find a Hopf bifurcation, and there was actually oscillations in the first moment or the total mass of the system. So there can be some system where you don't reach a steady state. So the assuming there exists a steady state is kind of very strong assumption. Yeah.
But you don't know how the steady state, what is the scaling with size?
No, the dynamical exponents. Yeah, we have not studied that. Maybe actually we have a plan to study.
I mean, I don't know the systems, but one possibility would be that the dynamical exponent vanishes when you have gelation.
Okay.
For lambda equal to 0, which means that you reach the steady state. There is a gap in your Markov matrix.
Okay.
Finite gap.
Okay.
When you have gelation, this corresponds to a finite gap, even in presence of lambda.
Yeah.
Suppose I just do a simulation,
Yeah.
let's say in 2 dimension or 3 dimension, and with some dynamics, I don't know what dynamics, but like I input again mass homogeneously everywhere.
Yeah.
And also this your evaporation happens homogeneously. I mean, in some regime, can I compare this with this mean field model with some kernel, or
so
is the kernel corresponding to that?
Yeah. So as far as I know that there is this diffusion limited aggregation sort of problem, and so for that cases, so what we find here, we find the mass distribution exactly in some cases, or we get the power law. But if there is space, so we consider also the spatial diffusion and etc., then it will be really complicated. So Rajesh, they studied one model where they consider space and they consider diffusion. So for that, as far as I know, they studied the renormalization group, and the exact probability distribution cannot be found in that case. I don't think that even in some limit, it will be really difficult. So, and I don't think there will be much correspondence. So like Samriddhi, they worked recently on this Smoluchowski equation, and they show that it is sort of invalid in the turbulent regime. So if you consider turbulence, but I don't know. So for example, the PNS paper I mentioned, they are brilliant of, they studied the mass distribution of the Saturn rings. So they have experimental data like which dates back to 1980s. So they have this data, and what they did, they studied exactly the same model with mu equals to nu, just that case. In that case, the exponent will be minus 3 plus beta by 2, and that matches quite well with the experimental finding. So yeah, so they are so as far as I've understood, so there are like water or ice made of ice particles, and when they collide, so depending on the energy of the collision, they can either aggregate or fragment or may just move. Yeah, so ice and dust and
It's a sort of dusty ring with
Yeah, yeah. So
Fragmentation typically is public in terms.
yeah, yeah.
Normally,
And
because of the velocity, normally
Boltzmann, so Krapivsky and Brilliantov, they have a 2009 paper in J-statement. They studied the Boltzmann equation, and they analyze the Boltzmann equation using different energy levels, yeah, and they get a Smoluchowski equation as 0th order term. Yeah. So there are some studies.